Hello and welcome to this session. The session's going to cover learning from disasters, the Bhopal incident in 1984, still considered one of the worst tragedies in the world ever, but also I want to look at it from the perspective of what we learn and also how we can perhaps use these investigative techniques to use those to assess probability, but also to manage high-risk environments in a better way so that things like this don't happen again. So, to give you an idea about it, the Bhopal disaster was a gas leak, MIC, so methyl isocyanate, but it wasn't just that, it had a combination of other liquids as a result of the vapor cloud, should we say, that transferred across in the locality. So Bhopal itself, central India, this particular plant was set up by Union Carbide, and initially it was built or started to be built in 1969. Took a few years to get it up and running, but then eventually it was, and then the methyl isocyanate was being produced rather than transporting it in, and that was one of the causes in terms of perhaps change and transfer. The gas leak did affect initially, although it's way underestimated, to 2,259 people with a death toll, but many have said since then it's probably more like 3,500, and then at approximately 8,000 within 2 weeks. So that again is probably underestimated. However, it's now thought that 1.4 million people were affected by this incident. So you can see how in time that's affected. And I guess even with those statistics, it's a little worrying. That officially claimed was 5,295 deaths, and then 25,000. But many activists have argued this, and like I say, it could be as many as 1.4 million. Children were born from the parents that were exposed, and they have defects. Quite a few of them were disabled in a variety of different ways. And so that in its sense is showing how it had longer term effects than the original thought. And eventually there was a court case, criminal charges, 7 employees, managers in particular, were imprisoned as a result of it. The effects of not just the MIC, but that combined, should I say, gas cloud created these symptoms. So, excuse me, you've got the ocular, which was a major issue. Quite a few people couldn't see for some time, if indeed they did recover from it. Respiratory, typically problematic if you're breathing in. Gastrointestinal, cause all kinds of problems with the stomach. And then there's the aftermath of the genetic issues. Psychologically, the stress and the anxiety associated with that. And then the neurobehavioral issues as well. So audio and visual memory, memory impairments, and then invigilance in terms of able to respond effectively to certain situations. So there's quite a few long-term, should I say, rather than just these short-term or early effects from the first 6 months. It's worthy of note to show some of the background to where Bhopal is, how it was situated, how it's grown in population over time. So since the 1950s to the 1980s, you can see that it's gone from 60,000 to 800,000 people. 500 meters above sea level, famous for its hills, beautiful fields and forests in the area that were, somewhat affected by this pollution as well. Due to its position in central India, it was a communication and a transportation hub, and it literally is position has made it that way. Consisting of tight twisting roads and markets and mosques and a railway junction. So there was not very much there, but mainly it's inhabited by poor families. And one of the key issues, I guess, that contributed to the spread of this was the kutcher houses, which didn't have lockable doors or closable windows. They were open to the elements, should we say, all the time. So it is typical of a slum environment. But however, if you think there's a cloud of a toxic gas coming over, there's no protection at all. So a lot of poor people suffered unnecessarily because of the makeup of the slums. So the plant was built in '69 for the purpose of producing pesticides, which was quite strange to put it there in India because there's a lot of resistance to it, and the sales figures didn't actually add up. But there you go, they went ahead regardless, and perhaps the idea was to maybe go further afield with the MIC or 7, as is the name of Union Carbide's variation of that. And eventually, should we say, from 1977 onwards, the push towards getting more tonnage prepared. So they went overboard. They asked for 5,000 tons a license for that, and they got it. But in reality, they probably only need 2,000 tons. And again, with MIC, it needs to be held under pressure. It needs to be a very reliable safety control system whilst being processed. And you need all these safety features built into it. And I think that is one of the key areas that we need to focus on when we look at the faults further into this. So since 77 and through to 82, then they were saying, well, it's not really picking up. We're not getting as much use as we thought. And typical of a US company, a large organization, they said, what we'll do is we'll make cutbacks, we'll save our losses, and we'll change things. So they took back some of the key engineers that perhaps were strong in the safety culture, had the right attitude, and then instead used a national, should we say, an Indian national engineer who was trained up in America, but definitely didn't have the experience. May have had the skills, but didn't have the experience. And if you couple that with India at the time, a growing country that perhaps didn't have in place as much of an understanding of chemical processing and the safety issues, or even the history in the area around some of the disasters that perhaps the US had learned from and maybe could have put in place to try and prevent this from happening. But certainly those key cutbacks made a big difference. One example was changing the steel to a more normal carbon steel rather than stainless steel, and therefore more corrosive, which again was one of the key concerns around this. Now, if the competence was there and if there were enough people around knew that this was unsafe, it perhaps would have been challenged. If there was a good communication system, perhaps with India and the US, in terms of Union Carbide, perhaps this could have been avoided. But it seemed to be that the US were kind of stepping away, back in their hands of it, away from it, and just letting things happen at their own risk. Now, I do stress, and I'm going to send you a copy of the lists of documents, but also the things that are available, videos and the likes of YouTube and other places. This particular one that I put at the bottom here, I really want you to have a look at. So I'll send the document that shows it. It is somewhat remarkable in the way that it's put together, and the specialists that have done this do a lot of work on investigating disasters. So they're coming in from an independent, they're not paid by the government or anything. It's and some would argue that that's perhaps a biased approach, but I quite like the way it's been put across and the guys that's put together. So please have a look at that. I'm not showing it basically because it's 20 minutes long, and I've had issues with uploading things on YouTube, so I'm going to stay away from it. The other thing I will say is this document that I'm referring to, and in that the Ashraf Labib is well, it's with Manchester University and Portsmouth. So a couple of the documents again that I'm going to send you copies of will show you that. I'm not giving you this book because it's £65. So what I've tried to do is say, well, maybe you can get the same information from reports that are available. So there are other versions. This was done in 2015, and I think Ashraf did his previous report in I think the early 2000s. but nevertheless, the details are very, very similar. So you don't have to go out and buy learning from failures, because there are PDF documents available that cover enough on Bhopal. Over and above this, if this plant was built in America, rather than going over to India, then the standards that you can see written in this have been put together in a guidance document that helps for making, or should we say, recommendations that can use for these type of plants. And therefore, if it was built in other places, even in the UK perhaps at that time, there would have been somewhat more effort put in place to make sure that it complied and continued, should we say, to comply. But again, like I say, the attitude was problematic here. And certainly the cutbacks and the unsafe changes and the oversights that were put in place led to this. So carbon steel pipe to replace stainless steel piping, removal of a number of safety devices. Safety devices should have had automatic backup devices, yet in Bhopal, these were manually operated. So we've just done a session on human factors, the human element, and you can see here that you've taken away a good automated system that would act as a backup, and you've replaced it with a manual version instead. Similarly, in the next one, the automatic leak detection warning system with a telephone backup support. That was taken out at Bhopal. There was no emergency planning measures, and I mean not just looking at the plant itself and the emergency response to the plant and a potential fire or explosion, but also, as you would have in COMAR regulations in the UK, what about the emergency services and what they could do to respond effectively and curtail the potential associated gas leak and so on and so forth. So there's that aspect. There was nothing in place, and the government were totally oblivious in many ways around this. One single vent gas scrubber installed. Yeah, now I'll show you the makeup of the picture soon. And what that scrubber does is neutralize MIC so that it's not hazardous. So that's obviously needed, but typically in these installations, there would be a ratio of 1:4, but only it was 1:1 in this situation. So quite odd as to how that's been allowed to happen. The flare stack that allows it to vent into atmosphere, only one again rather than two. The idea being that if one route to atmosphere was switched off by a valve or otherwise, then it'd have a different route that it could take. And there was no unit storage bank between the MIC manufacturer that it set up itself and the large storage tank. So you have the area where MIC has been created, then from that it goes into the storage tank, and from the storage tank it can then go out to the consumers, so it can be filled into the tankers, and off it goes as a pesticide. But that also acts as a means of assessing purity, so that if there is an issue quality-wise, then it could be investigated and more could be looked at. Again, a concern, should we say, from hindsight after the event. But there's also some other things as well that are worthy of note. Ashraf Labib quotes, prior to the disaster, training, manning levels and the education standards of employees of the plant workforce were reduced. Now, when I say reduced, what I mean is there's a turnover of staff taking place over that period. Between the 80s and 84, the plant's workforce was reduced by half. Yeah, so initially someone had said, we need X amount of people to run this plant, but because of the cutbacks set in place by US and the overriding company, they were saying, well, let's take some people away, let's reduce the cost to a minimum. But going back to the point I was saying before, they've also removed some of the automated systems that would have been there for safety reasons, and then there's a reliance on people. Well, if there's not enough people there in all the variations on a theme of shift work, how can it possibly react appropriately when that technology is not around? So that was a concern itself. The basic operation of the plant was further compromised by management decisions to operate the plant either outside its designated operating parameters, which it was doing more than it was capable of, or by the implementation of revised processes to ensure continued production while essential components of the system have known defects. And these defects have the potential to impact on the safety integrity of the plant. Now, you'll see as we get further into these root causes, you'll be able to see how unsafe that was. So taking that from page 50 of this book, yeah, and I guess that's the only bit then really, apart from 2 slides at the end, where I'm going to be quoting directly from the book itself. The rest is available in the documentation that you can easily access on the web. Okay, so a typical setup would have MIC being produced in a tank. From that production, it would then go via pipe systems into a bigger storage tank. And quite often they would have more than one storage tank. The MIC needs to remain cold, and it also needs to remain under pressure to act in its safest state. And then from that, it would then be moved on through a controlled pumped piping system to the consumer, right? So that's the typical process: production, storage, out to the consumer. But the other bits that surround it are all safety features to maintain it. So the refrigeration to keep the temperature low is absolutely necessary. The pipework that leads it either to the vent or to the flare stack is typical of this kind of setup. But in the process stack, should we say, and the caustic scrubber, the scrubber will neutralize MIC. So it will make it safe. So if there are any problems, or if there's overproduction and you can't safely store it, then there's an opportunity to get rid of it by putting it through the scrubber. Right. So all those need to be, 1, as part of the system, 2, available, and then 3, when the safety kicks in, for obvious reasons of process manufacturing, that the safe systems go alongside. And where it's preferred, and I know we're going back over 30 years now, but it is preferred to have a system that's on a computer that takes out the human element. And that way, if there's a valve that's not closed, there should also be something that tells the computer that the valve's not closing. Similarly, if there's a safety valve built in at the bottom and the top of the tank that says level and temperature, then it should have, and it should always be available, so that if anything goes wrong, you have an alarm, audible and visual, and then you have information that indicates what the fault is, and then appropriate action can be taken. Now, whether you class it as unreliable or problematic, but you'll see as we go through this, how it's been perhaps in a laissez-faire kind of approach, been misinterpreted. Now, I thought this was useful, and again, I've given you a copy of access to this. It's from the Bhopal Gas Tragedy technical series, and it's number 2. You know, there's 4 in total, but it's interesting to see. Now, I know it's an overly detailed piece of information, but just towards the bottom left there, perhaps you can see that it's got the MIC storage tank figure 1, and then everything else is built on top of the original design and setup of this. And what I'd like to show you is in reality that tank 610 is, as it should be, underground. And then, as well as it being under an earth mound, it also has a concrete layer to make sure that, you know, if there's a pressure problem, potential explosion, then that mitigates or reduces that potential risk. And then you saw perhaps the picture earlier on, and you see it in an open facility. And then you wonder, well, why was it underground, and why was it not protected by concrete surroundings, and so on and so forth. So as much as we would say that the design was perhaps at fault, is questionable. If I can now ask you to look at the top section, Table 1, MIC Storage Hazard Analysis. This is one method of a system hazard analysis as such, and you could probably see the IEs and the SAF links there. There's probably about 10 in total, but just past the description of things that have the potential to go wrong, you've then got another column, very much like risk rating in some respects, and it's about the probability of failure. Now, with these kind of analysis techniques, you will give credit should we say, to something that has had the forethought, and you'll potentially give it a credit of 1. And then everything else is below 1, looking at the unreliability aspects of it, or the potential for things to go wrong. And that's built into the calculation methods. And nowadays it's done on computer in an automated algorithm or calculation formula, and it will spew out the information you need just based on some usual facts. Now, with computers, the computer's only as good as the information that goes in. But what I've found is they're getting more and more and more reliable, because as the years go on, every time you do a little bit of cleaning, every time you do a bit of maintenance, if that information is imported into the system, then it will say the reliability of that piece of kit. So let's say in high ideal conditions, you have a safety pressure valve, and the manufacturer says that can withstand typical conditions, and the life expectancy is 5 years. So you can use that information, then say, well, that's the one. I don't have to change that for 5 years in those ideal conditions. But the more information you get, perhaps it's in a corrosive environment, perhaps it's in a high weather extreme environment, perhaps through all the maintenance issues, it then, because it's linked to this safety valve, identifies that 5 years is not good enough. Then you can use the factoring of the probability, and you can bring that forward and then say, rather than waiting 5 years for it to fail on us, what we should be saying is perhaps 18 months to 2 years, we should be looking at completely replacing that gauge or that safety valve or whatever it may be. And this is how information like this can be used when I say the term reliability, because it will help us to prevent things from getting to such a stage that we're constantly reacting to maintenance related issues. And obviously in the risk environment, particularly in process safety, the more maintenance you're having to do can either be a good thing because it makes it more reliable, or it could be questionable as to the amount of maintenance that's necessary to keep that plant efficient. Maybe we need to look again at the design or change it completely because it's not as effective, efficient, and as safe as perhaps it needed to be. So over and above that, I just wanted to show you that idea. But if you look at some of the bubbles of information that are in there, it kind of helps you to identify the things that will raise alarm bells and potential where things can go wrong. So just picking one out, rising pressure inside the tank would cause the vent valve to automatically open to prevent the internal tank pressure from exceeding 2 pounds per square inch. You know, so that's one example there. The engineers involved in that would be aware of that and make sure that the temperature is controlled and the pressure is controlled, as you expect in some of these systems. So there's things like that that will help identify the longevity, but also the reliability of parts and the working bits of the system. So hence, that's why I wanted to use this document initially, just to set the scene. Now, going back now to the wide list or long list of defects or issues that were perhaps the root causes of Bhopal. Okay, so first of all, the storage tank E610 was filled beyond recommended capacity. So again, think about the storage aspect and the fact that it needs to be under pressure to some degree and also refrigerated. The gauges should have provided warning of this and the process halted until rectified. So there should be something built into the system that says the gauge is telling us this, or the warning lights come up and we now have to take evasive action. Again, maybe people didn't know that, or they just became complacent and said it didn't matter. The storage tank, which was supposed to be held in reserve for access for MIC, already contained MIC. So the idea there is you shouldn't be mixing it, and therefore if that's out, then what's your contingency plan? And the contingency should be halt the job and don't produce, because you need that tank available. The reserve storage tank should have been empty, should have been cleaned, and there should have been a formal requirement that any production should have been halted until this had been established. However, the whole point as such, so stopping because you've been told that it's not safe, that wasn't in place. The control process didn't recognise it, and perhaps even if it was in place, it would probably have been ignored. The blowdown valve of the MIC storage tank was known to be malfunctioning. So again, there's this laissez-faire attitude around this in terms of, rather than replacing it with a reliable blowdown valve to make sure the job was effective and it did what it's designed to do, instead it was permanently up. So it should have been repaired, or the tank being removed from service until repaired. And if it is out of use and it compromises safety, then all production stops. So it's always putting safety in front of production, which wasn't the case. The danger alarm siren used for warning the adjacent residential communities was switched off, a normal procedure, after 5 minutes in accordance with the revised company safety practices. This just shows that it's inadequate. The emergency procedures needed to be in place, but also they needed to be constantly reviewed to see whether they're fit for purpose. And like I say, the government in India were very inexperienced in emergency responses of this type, and perhaps didn't have enough resources. So if you're going to give a license, perhaps the best thing would be to make sure that the emergency response team was on site, rather than having to rely on the local community response team as part of perhaps a license requirement. So again, issues around the way things were introduced and accepted. The plant superintendent didn't notify external agencies of the accident. In fact, they denied it initially, trying to play it down, hoping they could sort it out before things got worse. Obviously, this is clearly negligent on behalf of the management team, but typified the poor health and safety culture at that time within the plant. The authorities didn't know what actions to take in light of there being an emergency. So again, coming back to those procedures we were saying before. The requirements for good communications and the established emergency procedures was needed, and that interaction, as we would do in COMAR sites, whereby you can do drills and practices, set off the zones, gold, silver and bronze kind of responses dependent on the extent of the potential disaster, and so on and so forth. So those issues were woefully below what they should have been. The gauges measuring the temperature and pressure in the various parts of the facility. Now, bear in mind, as I've said before, some of them were removed, but these were notoriously unreliable, and the workers ignored them as a result of the fact that there was this tendency to say, it is another false alarm again, so let's forget about it and carry on. So the company should have had a robust maintenance regime which should have prevented this. Also, they should have had that safety culture where they put safety first. And they questioned issues around this and then said, well, we're going to halt production until it's been rectified and made safe. The refrigeration unit. So as I mentioned before, keep the MIC at low temperature and therefore making it less likely to overheat, and the expansion associated with that, the added pressure and so on and so forth. But there's also the issue around the shut-off valve for some time as well. All those came together. The issue could have only been resolved by the management having a commitment to safety and process guarding, as opposed to profit operation. Yeah. So completely upside down in what should have been in place. Carrying on then, if we go beyond that, then we look at some of the safety protection devices that weren't in place from a design perspective. While any local peer reviews of designs by local safety engineers was non-existent. So what I'm saying there is, if it was in the US or the UK, then there would have been something in place to check and make sure that all these design features were doing what they should be doing. They remained fit for purpose, and that it matched the guidance and the recommendations that were put forward at the design stage. But because of the distance, and maybe relationships as such, there wasn't that interaction between the head office and the need for auditing and inspections over in India. And as a result of that, standards dropped. Bear in mind as well, at a time when they're trying to make cutbacks and cost reduction also contributed to. So these causes were also of concern. The gas scrubber designed to neutralise any escaping MIC had been shut off for maintenance. Even if it had been operative, post-disaster inquiries revealed the maximum pressure it could handle was only 1/4 that which was actually reached in the incident itself. Similarly, the flare tower, designed to burn off that escaping from the scrubber, was also turned off, waiting for replacement of a corroded pipe. Again, alarm bells should have been ringing, saying we should be stopping this, and we should get rid of the MIC until we can make everything safe and bring it back up to standard. The tower was inadequately designed for its task, as it was capable of handling only 1/4 of the volume of the gas released, so similar to the scrubber. The water curtain, this is an interesting one. So we're talking now, this one caused the MIC escape. However, when MIC was billowing out of the top of the stack or the flare tower, they had a water spray system in place, and if it had hit the top of the tower itself, then perhaps that billowed smoke or the remaining gas would have mixed with the damp, and then it would have dropped to earth. So let's say the draft and the movement of the cloud would have been immobilized or significantly reduced. But instead, from the highest point of the full length of the hose, with the spray going at full pressure, it didn't reach the top of the flare tower. So as a mitigating circumstance and an emergency response, it was vastly inadequate. There was a lot of effective warning systems that should have been in place. The alarm on the storage tanks failed to signal the increasing temperature on the night of the disaster. And in fact, some would argue that it was never designed to check for temperature. It was perhaps just only a pressure gauge or an early warning system. So in that respect, from safety, we can learn from making sure we have the right type of gauge, the right type of warning system, the right type of safety features built into the kit, should I say, and the process safety itself. Okay, so with all those things going wrong, I thought it was worth then considering what safety engineers and BODs, how they get together and use hindsight, should we say, to try and identify some of the various factors. So it is an aspect of let's find out what the root cause is, but then how can we use that information in the future to prevent further disasters? And the fault tree analysis is one thing that's used a heck of a lot in high-risk environments. And you basically look at what potentially can go wrong, and then from that, what can we do to increase the reliability on safety? So then you do RBD in conjunction. So you have to look at FTA first. And from all the factors that come together on the potential failures, you then look at it from a reliability point of view to then say, well, how do we need to build on this extras to make sure it's even safer? So our friend here, Ashraf Labib, yeah, he did several studies on this. So this is the latest version in the book, but like I said, the documentation I'm using here shows you the study that was done by the 3 universities, Portsmouth, Manchester and Glasgow, around the disaster. And they showed a video of the incident, they talked about it, they give them some parameters, but then they let the students do the groundwork to then investigate, particularly from the FTA point of view, and some were then asked to go further and do the RBD. And within that, the 3 principles that were looked at were the feedback to design, what was wrong with the design itself, the use of advanced techniques for analysis, so FTA, RBD, and the other FMEA variations on a theme of analysis. So it could look at making better design in the future, and extraction of interdisciplinary generic lessons. So how can the industry generally learn from this in order to avoid disasters? So I think that's a big one for me, particularly in this module. So initially, this was followed by provision of techniques that can be used in the industry, FMEA, FTA, RBD. A brief narrative of the disaster was then provided. With the video, the participants were then divided into groups, and then they had to work together and individually to try and come up with the research. Each group provided an oral presentation, and finally, the author provided feedback and where possible revised and extended the models. So then you get that final document that was put together and made available, which was a half decent document then that could be used in the industry as a standard. So what happened in the initial investigation, or should we say various investigations, they focused on the 5 areas, 5 root causes. So you've got the vent gas scrubber, and the issues around that, the refrigerator not working and keeping the MIC cool, the slip blinds not installed. So this is part of the problem in terms of the materials, but also the safety gauges. But moreover than anything else, it's the pipework and the setup of the pipework that can send it to a safer state. So if you bear in mind what we were saying earlier, there was only 1 or maybe 2 provided, where 4 or 5 variations should have been provided so that the MIC could find a different route to a safer position. So there's those 3. Then in number 4, there's the water spray being inadequate. And then finally, in 2 parts, whether you class it as lack of safety or poor maintenance, it's the incompetence of the people involved or the lack of training or inadequate training that came together to really increase that potential. So in fault tree analysis, we use two gates. You have an AND gate or an OR gate. And you could probably see that at the top there, in the initial investigation, it uses an AND gate, whereas in the other areas, it's an OR gate. Now, some would argue that what we're saying is that rather than being an explicit black and white, yes and no kind of route with an AND gate, the OR gate says, well, what ifs, and the variations on that. And then you end up going down the sub-routes, should we say, to find out what the true root causes are within that model. So it started on the first version with an AND gate, where we're saying the 3 definites below that were poor design, lack of safety, and poor maintenance. But this was developed much more detailed. So what they said was they would rather it was an OR gate, because there was some debate, but they put an OR gate in the second version of this. So then it will allow the expansion of the what ifs and make it more clear, should we say, the things that went wrong. So if in a fault tree analysis, if the intention is to use it as a design tool, you need to analyze it first, and you need to use the information from it. So for example, a new design of a system, then it's better to be pessimistic and assume an OR gate. And that was part of the debate. Here you can see how they've changed that from an AND gate to an OR gate. And then when they've gone to the 4 areas rather than 3, so you've got ineffective workforce, failure of plant due to diminished design specs, poor management decisions, and poor maintenance of plant. So the obvious one there is the focus on poor management decisions, which many would argue that there's a lot of issues around that. And then, again, we've had an OR gate at the top there that now gives us 4 trackable options. And then you've got each variation on this. So this is figure 4. I'm going to show you figure 5, 6, and 7 over and above this. And then I'm going to do the RBD to kind of help us pull it together. So that was some of the debate that many would argue that from a design perspective, this is very useful information. So if we go down the OR route rather than an AND gate, it gives us those more options. And then it's hoped that we have better approaches. So if you look at the ineffective workforce, what you've got there is 3 areas: the quality of employees, the safety training, of the staff and the poor health and safety culture. Now, if you look at E being poor health and safety awareness as being a more specific understanding of this, you can then break it down in an and gate rather than an or gate and just say those two are typical for a poor health and safety awareness. So hence, at that point, it's got an and gate. When you do have and gates, when we come to RBD in a short while, you'll see the difference that we put in place in our decision-making process. So by using the OR gate for prospective analysis, rather than the AND gate for the retrospective analysis, it's a bit like Reason's Swiss cheese model. And therefore, things have to be in alignment, should we say. But with the right conditions, it can all happen. And that affects us in terms of our reliability analysis later. So in figure 5, and you focus on here on the plant being failing, should we say, stainless steel was replaced by carbon steel. No warning system built into it as an automatic response. There was no unit storage tank, and also that spray of the water was ineffective. But if you go just below that on F and G, you can then further subdivide it in terms of failure of plants. Typically, we would say the usual reasons for failure have to do with devices capability. So in this case, we're saying the safety device capability was impaired. And then in G, you've got the ineffective flow tower. So again, as a backup feature to make MIC safe and vent to atmosphere, that in itself didn't do the job because it wasn't available. So we've got 4 up at the top, number 4, 5, 6, and 7, and then you've got another 4 as a result of using the OR gates in trying to identify the features that were wrong. So quality of safety in terms of the safety devices reduced, also the quantity. So quality and quantity being questioned there. There was no redundancy or backup as to switch off, halt production, and what that would do and how you would do it. And then the incapacity or incapable of dealing with quantity of gases released. So that flare tower itself was not designed effectively. In figure 6, when we look at poor management decisions, you can see here that this is one of the biggest factors, one of the major root causes. So we've got 12 through to 16, but then we've got H, which focuses on emergency response deficiencies. And you could argue that, you know, in India itself, we're partly at fault in the government here for not making sure that happens. But nevertheless, you can see there that the majority has to lie with Union Carbide for not making sure that the decision-making process was similar to as it would have been, or perhaps was not in some respects, but should have been in place in America as well. So lack of awareness to the people about hazardous nature of the plant. So they didn't appreciate how nasty it was. The refrigeration on the unit was shut down. How they do that was not perhaps fully understood or allowed to be applied as it should be. The manning levels were drastically reduced, so that's a major concern there, particularly when you've not got the automated system to back it up. The storage tank, when you put the MIC in there, people need to know that the reserve should always be available. The plant being operated outside the design requirements and the specification, so that is a concern as well. And then 17 to 19, emergency planning, notification to the plant management team as to when things are faulty and what more needs to be done, so that there was that communication between India and the US. And then 19, the alarm siren turned off. Yeah, the management decision, the culture that existed. So big problems there, and many would argue that it was that stepping away, should we say, of management in US, but also this incompetence of the people working on the plant itself, because they've moved some of the key engineers off-site. And then the last part that takes us up to 24, we've got poor maintenance of the plant. And again, this was a major contributing factor. So we've got D that's put in place there, and then a further subdivision of J for the procedures on the plant itself, not being adhered to, not being doing enough. So defective blowdown, substitute engineering solutions, defective gauges, The slip blind process was omitted and there was no checking of the related lines. Now, some would argue that it's the incompetence of the maintenance engineers involved, and it could just be that they didn't know or they weren't effectively trained. So the combined factors of the cutbacks, the culture, the inexperience and the high turnover of staff led to the reduced number of maintenance activities. And when they're designing the plant, engineers and planners paid little heed to the importance of building in fail-safe devices to protect the Bhopal residents against this potential gas leak. Okay, so once you've built in, and as I said before, you've now gone from 5 through to 24 root causes in your FTA, you can then think about, well, what can we do? What can we learn from this? How can we improve things in general? So the first thing is with the combined approach to reliability block diagrams being built, you've got to make sure that it's independent of the FTA, but nevertheless, it uses the information. And Labib used his approach and set up these golden rules. So in every OR gate, in a fault tree analysis, a series configuration in the equivalent reliability block diagram is necessary. Adversely, rather than using a series on a FTA where you've got an AND gate put in place, then you use a parallel approach. And that's signifying that there's alternative things that can happen. To come clear when you see an example. You need to start from the top of tree and work logically through it, because that will help in terms of avoiding things that might be missed. Only model basic events. Think in the basic terms and don't overthink it. Just keep it to that. And the order in the reliability block diagram doesn't matter. So long as it's in there, it really doesn't matter. The important thing is that it's in there. And they always look for a real root cause. And the final one is the fault tree analysis and the reliability block diagrams are mental models for risk analysis. They're not risk assessments. They're a forward-thinking planning process to then say to engineers in particular and process safety companies to then say, well, how can we avoid worst case scenarios? What are we going to build in? And that's where perhaps, not just with Bhopal, but that's perhaps where we lose out a little bit, unless you have the government in place. They're in such strong position that they're able to make it happen before a license is given. So what I'm saying there is, with Bhopal, it was the inexperience of the Indian government in these areas that made them perhaps reduce the potential consequence thought process. But I'd like to think in the United Kingdom, particularly from COMAR as it's been revised a couple of times, that the general approach that's in there is, if I want to do process work in a refinery or similar high-risk environments, I need to jump through these hoops. And part of that is to notify in our case, the health and safety executive, that we want to use these hazardous substances that have the potential to cause major disasters. And in order to do that, we'll put all the information forward, and then to get a license, we've got to prove the case. So that goes forward then to a group of people that are specialists at the HSE who can work out whether that's easy to accept because the safety design is obvious and they've thought about the process, the FTA, and they've thought about issues that could go wrong and the reliability of it, the RBD. But having done that, they've then built it into the plant. And so if you then put a cost-benefit analysis in front of a senior management team and you're looking for investment to say we are building a new plant, then rather than it being considered a wish list, it's more a case of, well, we've got to do that because there's no way that the HSE would allow us to have a license unless we have sufficient safety protocols, backup systems, safety features in place, and also competent people in order to prevent disasters. So I guess I don't want to say it's, it's a learning from the failure itself, but I guess it is really. Do we have to wait for a disaster before we take on board? Well, if we look at fire in general, that's typically what happens in England, in the UK. We will wait for a fire, a serious fire, and then we'll change our approach to it. And there's usually legislation put in place. So a classic example was the Theatres Act that was brought in to protect people. We waited until, I think it was 184 people died in a theatre because it was wooden design and people couldn't get out safely, when on stage, used to illuminate the stage, was a light. That light was a candle. And shortly after that, the rule was that you must have a fire safety curtain on the stage itself, so the safety curtain can drop and the audience would be contained in a separate area from the stage, so it would minimize the impact. So that's one example. Bradford Fire led to sports grounds and improvements being there. King's Cross led to standards being improved underground for railways, and so on and so forth. And the learnings that we'll have from Grenfell now, and the changes that will be in the building designs and the building regulations as a result of it. So I guess, as awful as it sounds, quite often countries and governments need to be pushed down this route whereby we'll wait for a crisis, and then when the crisis happens, we'll react, and then we'll learn from it. So is it human nature? Most definitely. So I mentioned before about parallel and series. If you've done any electrical work, you might immediately see what I mean by that. But the top diagram shows number 2 and 3 in parallel, whereas number 1 is in series with number 2 and 3 being in parallel. From then on, if you look at the reliability for numbers 4 through to 11, all of them are in series, because go back to what we saw, they're all OR gates. And what it says is that if you imagine there's a valve between each one of these, if that fails and the next one fails, the next one fails, the next one fails, then it has a knock-on effect to all of them. Whereas when it's in parallel with an AND gate, it may well be that it goes through number 2 and the valve is switched off, but it has number 3 as its backup, so it can go through that way. So that's a safer state. So we look at these to see how we can build them in. So only a few parallel, mainly in series, as you can see from that. This arguably means that it is a higher risk. There's an accident waiting to happen. And if we're signifying a very vulnerable state, if any of the factors go wrong, there is a good chance of a disaster when you see it in this state. So engineers that design these think, oh my word, everything that's in series there, we're going to have a disaster. Therefore, our design of safety features needs to communicate with us, needs to tell us when these things aren't as they should be. So that can be used, and that information can be reviewed in terms of probability. And that's basically what it is. Reliability put side by side with probability will affect our decision-making process, and which will ultimately will help prevent a safety disaster, but at the same time will improve it by design and communication so that these disasters are avoided. Now, to really go into depth, I did mention there's 2 other slides that were taken from this, and this is the 24 that I mentioned before. If you look at the failures there, I'm not going to go through each one, but you can see the probability is analysed in the third. So they've done qualitative and quantitative methods. So those calculations move from a basic statement. So number 1, the quality of employees was reduced. So people moved on. The people that were recruited to take their place, perhaps it wasn't the right caliber, and there was no way of checking that competence. So as a result of that, over 5 years, it's then increased the risk significantly. And then you've got a reduction in people and a reduction in competence. What's the potential? So they use a formula to then work that out. And then the right-hand side indicates the actual value of probability. And as you can see there, they're all quite high. And as a result of that, we can then say what we're going to do. So when you start going through this and the next one, you can see then that it all needs to be looked at and identified and then said by the engineers in order to make sure that the MIC that's being stored in the backup storage tank, we need to build it to a certain specification. We need to build it with pipes and valves that are a certain specification. We need an alarm system built in with a certain specification and reliability. And as a result of that, the calculation of the values change the numbers. And the numbers then bring it down to less probability because of increased safety features and changes in design. So all of that helps to make the overall judgment, but ultimately prevention. Let's not wait for a disaster to happen before we then learn by hindsight. So the key idea I was trying to get across there was just to introduce you from one disaster, Bhopal, and a couple of the techniques that's used. And ultimately, what I want to do is to get you thinking beyond that point, to then say, when you look at the myriad of other disasters that have taken place, and we look at other aspects of the module, what actually went wrong is important. But then secondly, what can we do about that? And what we learn from it, and how can we make improvements? And that's the true learning. So prevention, longer term, what we've learned from the past, hopefully will make a big difference. And as a result of those learnings, we can become more reliable and we can reduce the probability of a disaster happening again. Thank you.